I hope you guys enjoy. All right.
I wonder what tipped that off.
So, my name is John Kilogram, and I'm a senior here at FIU. I've done a fair share of work with machine learning in the past. I'm going to be giving the workshop in PantherHacks 2020, and I'm here accompanied by my colleague, Hermes Bonilla. Hermes, you can introduce yourself.
Hey guys, like John said, I'm Hermes Bonilla, and I'm really glad to be able to co-host with John today on the machine learning workshop. And thank you guys for coming out already. So let's get into it. So what is machine learning? So before we can answer what machine learning is, we have to go back a bit. Machine learning is a strand of artificial intelligence, and artificial intelligence is really an umbrella term. Like its broad definition is that it's automation of human tasks. So then from that we can derive machine learning, which is a subset that's more data driven. So whereas artificial intelligence is programmed and more guided, machine learning derives its experience from the data that it gets. And then deep learning, we'll touch on it a bit later, but it's just a subset from machine learning. Okay. So this is Mr. Alan Turing, and a personal icon of mine, and he's considered the father of artificial intelligence. And what he's explaining in this quote is really the goal of machine learning. And that is that we want a machine that can learn from experience. And the goal of machine learning is reached through having data sets that you run through. And we'll get going on that in a bit. So before I start the clip, PantherHacks is a COVID-19 themed hackathon. So it's only appropriate that we go over some really interesting machine learning applications that involve COVID-19. So the first one that we're going to touch today is a face mask detection by Troy Labs. And before I start the clip, the box that you see is called a bounding box. And it's normally used to bound things like a face, an object, a person, and it's really for humans to see what the program is trying to focus on. So as you can see, it's going through, and it's real time, looking at the camera footage. And it's really that simple. And maybe some of you guys can benefit from doing that into your hackathon project. So just something to think about. And then another COVID application is this, which is actually, it's built by Landing AI, and it's highly complex, but there's ways to do it with tutorials and so on. So what it does is we can see the input, which is a CCTV camera input on the left, the top left. That's what the normal camera is seeing. So, you know, just like human eyes. But on the bottom right, we can see the same footage being passed through a model. And so what this is measuring is social distancing guidelines. And we all know how important that is in COVID. So then using machine learning and artificial intelligence to do this is great. So it's pretty accurate. If you see, it measures out the distance between each bounding box and figures out, okay, are they in social distancing guidelines? And if they're not, you'll see the contrast of the red, and it's linking them together, saying these are the people that are violating the social distancing. And on the on the left of the bottom GIF, you can see that it does more than 2 people. It can do an entire group, so it's highly effective. So, and then the pipeline for the cough detector. So this is really a general pipeline for most models, and the most important step, in my opinion, and also the longest step normally, is the data cleaning. So you want to make sure you have clean data going into the model. And by clean, I mean it's organized so that it can be taken in from the model, that it's balanced, and therefore has no bias. So what bias is it's any kind of, well, bias that's being affected on the model. So having unclean data can cause you to have results that aren't accurate, and that's not what you want, because when you're training, you want to make sure that whatever experience that the model gets exposed to, it knows how to react. That's really what we're doing here. So then after data cleaning, then you have to build the model. So the architecture that you want, different type of neural networks and so on. And then you want to train it. So I'm going to get into some of the data cleaning, and then John will later get into building the model and training the model. So this is how we originally got our data set. This is a data set from Google. It's the audio data set. And it's done through an Excel spreadsheet, or what's called a CSV. And there's some initial problems that we see in this data set that we need to clean. The first being the first cell and second cell. So in Excel, you have these cells. So as you see on the left with the indexing, you can see which cells I'm referring to. So the first and second cell, while they're helpful and they give us data about the overall data set, we don't want that, because when we're feeding it into a model, it makes it a lot more complicated. And so that's something that John and I saw when we were cleaning the data. And so we got rid of the first 2, and then we tried again. And data cleaning, you have to keep trying and seeing what works and what doesn't. And we saw another problem that's a lot harder to fix, because the first 2 cells is easy, you can manually fix it. But then with the quotation marks, as you see in the labels, so there's different types of labels and different lengths, and also one video can have more than one label. And the labels are just referring to what's happening in the audio set. So the problem is, when you're trying to feed it into a system and you're trying to clean data, you want to try to make the data coming in as uniform as you can. So the problem with this is it's not uniform, because there's different types of lengths of labels, and so therefore the quotation marks are in different places. So we can't just say, well, ignore the quotation marks. But what we did is we had to create a script. And as you might notice, the full data set, as I said, was 22,161 cells in total of data. And so you could technically go through it by hand, but I don't think anybody has the time or will to do that. And so you have to create a script. And for those who don't know what a script is, it's just think of it like a little program that goes through the data and does some changes. And so we did that. And what we got is new usable data. So this data set is fine, except there's one more problem. If we look at cells 2 through 8, we see that the YouTube ID, there is no YouTube ID that we can use. So that data to us is useless. because even if it has the labels that we want, we have to find some way to get rid of them because we can't find the original video. And so there's two ways you could do. You can include that in the script and get rid of them overall. But how we decided to do is just ignore it for now, and I'll show you how we dealt with it. So just some quick code. The main reason I wanted to show this function is this is part of our data cleaning script. And so we can use it for two things. One, if you look at line 29, you see that we created a variable unknown equals the name that we saw in the previous cells 2 to 8. So like that, we can do in the if statement on line 32. We can tell it to ignore. Just forget if it has unknown, don't consider it into the function, right? And so what's special about this code, which continues down into the next slide, is as I go back, I'll show you. If you look at lines 31, we commented there that that if statement is going through and finding our cough label videos. So the ones that have coughing noises inside of them. And so then in the second one, line 39, you can see that else if statement is our non-coughing data. And so how this helps us is it's used for balance, and balance is very important, like I mentioned before, because without balance you have bias. So I could be feeding my system nonstop cough data and think, okay, well, it's bound to find what a cough is because it knows that what a cough sounds like. But it's probably then when you expose it to data that's not in your training data, it's probably going to hear any noise and think, oh, that's a cough. And we don't want that. We want to include in the mix, we want to include some non-coughing data so it can distinguish between the two. And so then we also created a dictionary of items that we need in later functions and so on. And so then this is our main function. And that's really the last piece of code that I have for the data cleaning. But this just ties it all together with all our other functions. And it's just like a nice package that we can run and get all the data that we need. And then so the next slide is feature extraction. And this slide I will give to my colleague, John.
What's up, everyone? Hope you guys are following along. So the next phase in the pipeline is generally arguably one of the most important, like after you've gathered your data. Now you want to know what information or features of that data do you want your model to account for when it's learning. I use model like in algorithms. You'll see me use these two terms loosely or interchangeably. They essentially mean the same thing. So a little preface to the demo that we're going to be doing. There's this guy named Seth Adams. I encourage you to check him out on YouTube. He's an audio engineer, and he's the one that like kind of like started this workshop demo. It's spread out about like 3 hours long. He has like a more in-depth demo that's a little bit longer. I'm just going to condense his ideas down to the remaining time we have left. So feature extraction. Typically when dealing with sound, for example, there's certain salient features that makes the sound distinguishable from other sounds. What are these sounds? Sounds, typically how computers process them is as waves, frequency over some time domain, or it can be frequency and energy, like as you can see above, which shows a spectrogram across a time domain. This is actually common, which we are going to be using to input sound data as an image to see if they can classify it based off this null frequency coefficient. There will be a function that kind of like already initialized in there when I start up the tutorial that you guys can like kind of code along. It's kind of there. The weights or the parameters are already set when I start sharing my screen. So you know, like it's just the baseline way to get null frequency coefficients. I don't know about signal processing that much, so we're just gonna view like the null frequency coefficient process as kind of a black box model. Again, I encourage you to look at sub-atoms. What we're going to be focusing on is building them all. So for the first part of the feature extraction when dealing with sound waves is removing something called noise. So you've probably heard this term a lot when you talk to engineers or signal engineers. Noise, what is noise? Well, noise is essentially background information that's captured by some type of module that we don't necessarily care about. An example of this is like if we're trying to detect coughs, like that's me coughing, but then like let's say there's something playing in the background, right? We don't care about what's going on in the background. We just care about like the actual cough, like the actual person like feeding their sound waves into the model. And there's a bunch of ways to like kind of get around this and a bunch of techniques that I encourage you guys to check out. But for our use case, we're going to be using something called enveloping, which is a signal processing technique that removes dead spaces, which is considered as noise across like a frequency domain. So what this function typically does in common signal processing tasks is you have some sort of threshold, a frequency threshold. Let's say we don't want quiet noise or like noise that we don't really care about, like low peaks, super high peaks or super low peaks. In this case, we're doing super low peaks. We can set a threshold as like, okay, if our frequency goes below this parameter, we're just not going to include it, and we're going to truncate it from our audio signals. So this removes like kind of like quiet spaces in between like audio signals. Another function that you see right below the envelope feature is the mono converter. This basically unifies the channels of the audio sound, because audio can be like dispersed through multiple channels. We only care about one channel. We want one sound source. Like we don't care about like different like fluctuations in different channels. Like we don't have, the computer doesn't have two ears. The computer has, you can view it as two ears, but like for the sake of simplicity, the computer has one ear. It just wants the sound information. It doesn't care about multiple channels. And this is the function that converts it to one channel using the toMono function from the scikit-learn library. Going back to the envelope, you're wondering probably, like, what is this? Like, what is this series rolling? It's essentially a sliding window technique. So obviously, signals are like fluctuating up and down. If we like step through each signal, we can be removing a lot of important information. So what is usually done is like we take a window and slide it across the sound waves, and we take the maximum of that window, or it could be the average. In this case, I'm using max. And if it's in that window, if there's nothing that exceeds the threshold, we're just going to denoise it, like remove it altogether, because that window isn't important for us. Doesn't have the frequencies that we're looking for in order for us to make the decision. If you can go to the next slide, please, Hermes. So the tools that we're going to be using for the demo is the TensorFlow framework. I'm sure some of you guys may have heard of it. It's a very popular deep learning framework that abstracts a lot of the neural network architectures for us. So we don't have to like build like a custom graphing class and like build custom gradient descent algorithms. Why reinvent the wheel when you could just use them? What we are mostly concerned about is like how these layers, or how the connections between the nodes interact with each other. We're also using pandas. For those of you who went to the pandas workshop, it's a useful tool for data processing, actually. It allows us to, Adrian, no, we are not coding from scratch in C. We're coding in Python. I wish we can code in C, honestly. Sorry, I'm just responding to the question in the chat. But pandas is pandas is a cool tool that allows us to interface with create like these abstract data structures for us to like analyze data more efficiently. This little sad looking fish up there in the corner, this fish looks like, man, like the owner's not feeding him. But that's actually the GitHub user who creates the Capri library. Capri basically is an open source software that's available. This developer who actually created it actually works for Spotify. And if you don't know Spotify, like machine learning engineers are like top notch like these days. This guy found a way to compute mel frequency coefficients, ingrain them in the training process, and published a research paper that actually showed that it actually has a little bit of overhead, and it's probably more advantageous to just compute them during training time rather than loading them in and like trying to store the data and compute them onto memory. We're also using NumPy, which is just a way for TensorFlow to fastly compute matrix and list operations. We're using Librosa, which is a very popular framework, or library, I shouldn't say framework, that allows us to process sound and do a lot of the functionalities in extracting Fourier transforms and mel frequency coefficients. And if you can go to the next page, please, Hermes. We can continue. Give me a second. All right, cool. So we are going to use something called a neural network. What is a neural network? I hear it thrown a lot. Essentially, the most basic way I can explain it is a computational graph where you pass in some sort of vector through it. This vector is propagated forward, and with some initialized weights, it gives us a prediction. Now, once it reaches that prediction, it's first randomly initialized. It's going to compute something called a loss function. This loss function will tell us how wrong this graph, or like how badly this graph's weights and biases are initialized. Weights and biases are essentially the factors that we account through each node transition. So like if you can look at like from one node, you can see like a line to another node. There's typically an assigned bias, which is like if you view it like in mathematics, like simple 2D plane, bias is essentially like the y-intercept, and it also accounts for the weights. The weights is like how much is it factoring in like this node connection pair. And then once we get this loss function, we use an optimizer algorithm in order to calculate how wrong we were in making our predictions, calculate how wrong our weights and biases are initialized. A very common optimizer is a gradient descent optimizer, which uses first order differentiation in order or inverse first order differentiation, because those calculus nerds out there knows that when you take partial derivatives of a function, it actually points upwards. So if we like point it downwards, we show ourselves the path to like minimize the cost function. And then this is propagated backwards through a back propagation algorithm, which then like updates the weights and biases through each node connection pair backwards, and make sure that it's all initialized optimally for that first partial differentiation step. If you can go to the next slide, please, Hermes. So the neural network that we are going to be looking into is convolutional neural networks. And you may be wondering, like, what's a convolutional neural network? Like, John, you didn't really explain neural networks that that well, how can it even be more convoluted? Well, convolutional neural networks is essentially a neural network with just a few extra steps. You can consider this feature extraction. Technically, it is. It's the model, like given an image, we extract salient features from the image. We can, through a series of pooling and convolution layers, which gives us a representation of the image that we are concerned about, and feeding it forward into our actual dense layer or regular neural network. Yes, convolutional neural networks are the same models and algorithms being used to detect your face and detect who you are in surveillance cameras. China's using it to track its citizens, and I wouldn't be surprised if the US is using it too. So if you could go to the next page. Demo time. What? So it's either you're really scared to like start coding, you're like, oh man, this seems complicated, or you're just like, bring it on. Like, I don't really care. I already know all this. So I'm going to share my screen through my other user who's connected on the Zoom link, and we can get started. Give me 2 seconds. In the meantime, Hermes, would you like to entertain any questions while I get set up?
Yeah, I'd be happy to.
All right. Anyone have any questions? Please voice them, and I will answer. But I'm going to be focusing on like actually setting up for the demo.
Yeah.
It's going to take 2 seconds. It won't take that long.
While we're waiting, something about the CNN, or convolutional neural network. It's meant to simulate almost how eyes work. So you hear CNN often used for really vision tasks, like John was saying. And there's really a lot of different architectures. That's why it's also so useful to know artificial intelligence, machine learning, and deep learning. But okay, Danielle Cardenas. Where do we place the audio files that we downloaded, the 2 gigabytes?
I'm going to get there. Just give me 2 seconds. I'm just, as you can tell.
Yeah,
I'm just making sure like it's easier for everyone else once we actually get started.
The stuff that we downloaded, it's mostly stuff that you need to use for the actual coding. And if you don't feel like doing the coding, that's fine. You can just go along. That's fine. You don't need to be coding along, but I always prefer to do that. So there's John.
All right, guys, can you see my screen? Oh, let's field this one more question. I think we missed it, but are we working with raw sound data, or are we computing on some sort of? So we're going to be working on spectrograms, as you can see on like this code that I already have up semi-initialized. We're just going to be like given a MEL spectrogram of the sound data. We're going to input this into like the actual network. Yeah, so we're not working on Fourier transforms right now. I wish we were. All right, cool. So let's get this show on the road. So once you downloaded the audio files or whatever file you downloaded, maybe it was some other data set you wanted to test. We are going to put it in, excuse me, kind of like have this thing all over the place. We're going to put like the WAV files in this folder. So once you have it downloaded, I have it downloaded somewhere else. I think I have it here. Yeah, I have the WAV files here. So you can extract whatever WAV file you downloaded. Make sure it's in a folder called WAV files. And once you're done, you can just put that WAV file folder into the clone directory that I asked you guys to clone. May take a little bit because it is a hefty data set, but shouldn't take too long. I have pretty trash internet, so if it's going fast for me, then it should be going fast for you guys. Alex asks, each node in the hidden layer has a weight for each input value it receives from the input layer or another previous hidden layer. the sum of these value weight pairs then get into a logistic hypothesis function, like a sigmoid to yes, Alex is exactly correct. So I forgot to mention the activation layers. That's really important. It's each node has like an activation layer, which is helps us understand like the value it's receiving. Activation layers can include some common ones are sigmoids, which produces a value ranging from 0 to 1. Others is ReLU, which produces sigmoid produces a value from 0 to 1. ReLU produces a value from 0 to infinity. And then tang H produces a value from -1 to 1. Just a way of just condensing the data or the input that we've received in order for it to be more understandable through like each node pair. All right, so the first thing that we're going to do is like once in my clone directory, create a file called models.py and download these dependencies. We're not going to be using time distributed for now. We can just comment it off for now. We're not going to be using time distributed. There's another, we can use a one-dimensional convolutional neural network considering like across the time domain, but for now we're just going to look at the image to most basic bare bones neural network. Yeah, so if you guys can like follow along, copy this, make sure it's models.py, make sure it's in the same directory. I'll give you guys until 3:34 to get this done. But one thing that I wanted to like clarify, so there's, when dealing with neural networks and convolutional neural networks, there's typically, John is using it later in the, yes. There's typically different types of tasks that we can do. We can do simple classification where we feed it an input vector, an image or whatever, and we just want to classify it. What is this input vector? What class does this input vector belong to? And then, like what Hermes was showing, there's a little bit more like application that you can use these convolutional layers for, and this falls under localization. This allows us to localize which frame in the actual input vector or image that the person is classified on. You usually train this through like it takes a lot of labeling, hand labeling a lot in order to like get the bounding boxes, and then you like feed it into a some sort of data processing pipeline that interprets this in some sort of structure in order for us to use it in the neural network to learn like localization in an image. There's also segmentation, which combines localization, but it's a pixel by pixel based model where it calculates the classes or instance of a class of each pixel and tries its best to like annotate each class and draws like a mask over the detected person or whatever object you want to detect. But we're just doing classification. This is just to get our feet wet. And yeah, let's get this started. So it's now 10:34. As you see here, I imported TensorFlow Keras layers, which is essentially a library that allows us to abstract layers in a neural network and define each layer in the neural network set that we're going through. What is it? It can be a conv layer, it can be a max pooling layer, or it can be a flattened layer. I'll discuss this as we go on, but just bear with me for now. And then we have TensorFlow Keras models. Model, this allows us to initialize a model object, like some sort of weight, like model weight that we're going to be using in order for us to feed in our layers or initialize based off like the network architecture that we create into like this model class. It's abstracted, right? So yeah. Any more questions? The biases are essential. Yep, Alex is helping me out. He's also on my Discover team, so he knows the stuff. And then we have regularizers. So as you guys may or may not know, in machine learning, Hermes alluded to something called bias. There's also another problem that's overarching, and a lot of machine learning people experience it, and it's called overfitting or underfitting. We can have a model that generalizes a little bit too well to the data that we have and strictly adheres to a function based off the data we have. So the implications of this is it may be perform extremely well for the data we have, but when we feed it new data, perhaps it's in the same classes or like the same distribution of classes, but it's a little bit different or augmented, the model may not pick it up as easily as the data it's been trained on. It's too tightly bound to the data that we've trained on. So we use something called regularizers or regularization, a technique that allows us to drop randomly drop different node or randomly drop different node connection pairs by some factor as a loss function in order for us to learn, add more bias for us to learn generalizations easier in the data that we have. So we make sure it's not fitted too strictly to the data that we're passing through. So that's regularizers. And then we, this Capri model, this is the sad goldfish library that I was talking about. This allows us to call like this null spectrogram function that we have here. And during like the model training, the spectrograms is also computed on during the actual training instead of offline, wasting up memory time. Then we have normalization, which is essentially what we want to have. So we have, let's say we have data, and it was super easy. Let's say we have cats and dogs data, for example. It's super easy for us to get a bunch of images of cats, but not so easy to get dogs. What do? Do we truncate the dog data and try to make it balanced for like cats and dogs? No, more data is generally good. Instead, what's a common technique to like kind of bypass this issue is a technique called normalization, where we have distributions of each classes and we try to like map the distributions normally across like centered around 0. So it's kind of like if you guys are familiar with statistics, a normal distribution or a Gaussian distribution, where it's between each class. And then, of course, we have a Boyd TensorFlow. That's our library that we're going to be using to build this model. And then we have OS, which we're going to be using to read directories and stuff. We are not going to be using OS here, but it's just there. We can comment this out. It's not that important. So yeah. So the first thing that we're going to do, once we receive the spectrogram inputted as X, we have our input. Actually, let me start from the beginning. So what I did here was initialize a function called com2d. Our number of classes, what we are doing is building a cough detector or a sick detector that has sick or no sick. So given like respiratory sounds, coughing, sneezes, can you determine if they are sick or not? And we have our sampling rate, which is like across like frequencies, like how many frequencies is considered like 1 second, like, or how much of this data can be fit into one hertz or per second. And then we have our delta time. What are we looking at? Our delta time is 1 second. So this is like, we want to do comparisons of 1 second. It doesn't take that long for us to cough. Like coughing takes like less than a second. So that's why we're using 1 second. And we input this into layers.input, which we initialize our input as a 3 actually we initialize it as a tuple, where we have our sampling rate by delta time, and 1 is just the way Keras likes to see things. And we're initializing this as our input. And then our Mel spectrogram coefficient, like I said before, I'm not too comfortable on like giving you guys signal processing 101. So we're just gonna internalize this as a way of us getting a pictorial representation of the image. So our next step is taking our input x, and we're going to normalize it. Like I said, x can be unevenly distributed. So we would want to call the normalization 2D method and normalize this based off batches. One thing I forgot to mention was that neural networks are typically passed in by batches, which is like, because you don't want to feed in your entire data. That's number one, like that's a lot of computational overhead, and number two, it's better for us to learn like through chunks, so we can kind of like map as it goes through each batch, map as it goes through each batch, like on plotting, and like kind of like keep track of like the losses and accuracy or performance metrics. We can just give this a random name. We can just call this normalization or batch norm. Batch norm. And this is essentially for us to get the, like, see, like once we run this, we can like have the option to see like the initial like layers of the actual network that we're building up. And this takes in our input vector, and once we go from there, we have a now normalized distribution of data with this function. Now, one thing that we should be wary of is, actually we don't actually need this anymore. Now we should go to, now we define our layers, our first layer after we do our normalization. It's the conv2D layer. So this is a convolution layer, which is essentially a layer that extracts sliding window. It doesn't downsample or upsample at all. It's just a window that extracts features across like a sliding window of a matrix that we are interested in looking into. This convolution layer, the first parameter is usually a filter. This is how many features we want it to output. So we just want it to learn 8 features for now. You can do like whatever. I'm doing 8 just to be safe, following the guide. So these are the features that we are extracting through this actual convolution. So the sliding window is actually called a kernel in convolutional neural networks. And we can just initialize this to any size. The guide has it as 7 by 7. You can do anything that, as long as it's not too crazy, that would affect your performance. I think it would be a good experiment, so we can kind of like see how it works. And then we have our activation layers. Alex alluded to this in the chat. This squishes our data into something more digestible, so we can have it across a distribution. As values get more extreme, we want it to be weighted less. So it's like, oh, it's extreme, it's just extreme. Like it's with all the other extreme classes. We only care about like between the zeros and ones. And then we have padding. This is essentially like once we go through the convolutions, like what's the step size between those convolutions? Do we want it to go 1, 2, or like just the same as like the actual of the actual image? So it's like stepping by 1. So we can just call like for simplicity's sakes, we can just like initialize it as same. I recommend looking into the documentation of the Capri library. It basically discusses like these inputs a little bit more, and you can view the code and see how it's like implemented. It's pretty cool. And then we can name this some random name as well. Hermes, please interrupt me if there's any questions. I'm looking at my main computer because my laptop is actually pretty slow, so I can't really.
Yeah.
So this is Com2D. We can just call it Com2D tang. And then we have the input layer as X. So the reason why I'm using tans H, for example, for this first one is that we don't want to use ReLU because, like I mentioned before, ReLU excludes negative values. So it only goes through 0 through infinity. We want to keep the features between like -1 and 0. And then this would allow us to keep more features of the image for our next layer that we can use ReLU, which is a very standardized activation function for convolution layers. So our next layer is actually going to be a max pooling layer. We want to downsample our data, right? So by downsampling, we are able to extract only important features and get rid of features that we don't really care about. So like we don't want the entire image. If we don't have this max pooling, the actual network would take forever to run. Layers max pooling. That would have been an error. See, this is me doing that. So that would have been an error if I didn't catch that. But it's layers max pooling, and then we can define a pooling size similar to kernel size. This pooling size can be small for now. We'll call it 2 by 2, so it's a square of size of area 4. Padding is the same, and it takes in another parameter called name, which we can call whatever, and call this whatever. Let me not be lazy. Padding. And then now we are going through our next convolutional 2D layer. What we can basically do from here in order to add more complexity to this neural network is just copy and paste these like 2 more times. And this is just a series of like max poolings and convolutions, which is extracting more and more features that we care about. Let's scale up by a factor of 2 each time. So like we're going to take more and more features as we go along. So over here, it goes 16. And then once we go 16, we are going to take, once we go 16, we're going to take 8, 7, 2. Once we go 16, we're going to decrease the window size by 2 as well. And then increase this, we're going to increase this by 1 for each one. So this one increases by 2, so this stays 4. The way this guy has it is that's 2, 3, 2, 3. Actually, this com2d is actually 3. You can initialize it anyway. I'm going off of the tutorial. This guy has it's 3. So 5, 2. Forgive me. 7, 2, 5, 2. 7, 2, 5, 2. Then we have 3, 2, which we have. And then we are going to do, so com2d max pooling, 1, 2, and then let's do this 1 more time. We're just basically adding complexity to our network. We're just adding more layers to the actual convolutions. This one scales to 16. This one scales to 32, and we're going to cap it at 32. So this one stays at 32. And then this is 2, 3, 3, 2. Max pooling is 2. Let's get rid of this max pooling. We don't need this last max pooling. And this is actually good. We don't need the max pooling because we don't want to like downsample it even more, like this guy has. Let's kind of name these 1, 2, 3. So like they're all uniquely identified. Common mistake that I had made in the past. So the next thing we want to do, like I said, we extracted our feature vector. This feature vector is extracted. It's not linear, so it's like matrix, or it could be more than a matrix. We just want to flatten this for the regular neural network. So a simple way to do that is using the layers module, and you can just call it flatten. I cannot type flatten, and then we can just have name is equal to flatten. And then we pass in our vector that we're passing forward. And then once that's passed forward, we're going to use a regularization called dropout. This is a technique that I alluded to earlier for regularization. We're just dropping random weights in order to like make sure the model doesn't overfit. So we can just do x is equal to layers dot dropout. Oops. Dropout, and then our rate, which is just the factor that we're going to drop out, or like how much we're going to drop out. You can just call it 0.2 for now, because keep in mind it is a loss function, a mini loss function I like to call it. And we can call this dropout. And yep, we have that dropout. And then now we're gonna, once we like dropped it and like normalize the weight distributions a little bit, this incentivizes, this like drops input neurons, which allows us to like kind of like make sure the distribution of the neurons is more evenly distributed. So once we have that, we can just finally pass it through our actual layer. Excuse me for that mistake. We can do it. Dense is just a regular convolutional architecture, and we can have it as 64 activations. We can have each activation be a ReLU function, which squishes our outputs of each value node pair. And then activity regularizer. This is like regularization. We're just adding a factor of like how much, like once it's picked to drop out, by how much do we want to drop it out? We can just drop it out by, we can drop each layer to, I cannot spell activity regularizer. Sorry, regularizer. And then like we'll take the layer or regularizer, and for each one that's picked, we can drop it by a factor of 1.001, which is following the tutorial here, people. And once we have that, we can just name this dense layer. Yep, so that's our dense layer with regularizers attached to it. Now what we want to do, so neural networks in general produces some sort of output at the last layer. What we want to do is like squish this output into our class labels and encode it to our class labels. So what we can do is like I mentioned before, a number of classes, we can just like use a one-hot encoding. We can call this output, and then have this as dense or layers. No, we have output and we'll have it as layers, not dense. And then once we have the dense layer, our dense layer uses the softmax layer as an activation function. So this just squishes it to the number of classes that we have, which is 2 in our case. It's coughing or no coughing, sick or no, not sick. And I said software, didn't I? I'm a mess. And then we can have the name as, just whatever. Softy. I'm gonna call it Softy. And then now we initialize our model object. We initialize the parameters that we initialize what our model should be like ideally. And our inputs is I, output is, or outputs is output, and we have name, and we can call this 2D comp neural network. Sure, Mom. So we built a neural network. Yes. We have any questions?
I think we do, but in activity regularizer, you put an extra A. Just letting you know. Might cost
Thank you. Thank you. Thank you. Thank you. Yes, I did. Thank you.
Yeah, Alex had a question. Do you want me to read it to you, or?
Yeah, can you read it to me?
Yeah. So he said, so regularizer sets the regularization parameter to ensure that the model doesn't overfit the data.
Yep, exactly. That's all the technique is for, to make sure that the model isn't learning a little bit too well on the data that we have. I mentioned gradient descent, so I'm doing the model.compile. This actually runs our model. I mentioned gradient descent. A very widely used one is optimization algorithm is Adam. This uses a bunch of other, it uses mini batch gradient descent, I believe, and a bunch of other optimizations as kind of like utility functions in order to like produce like a super accurate or hyper accurate optimization function. This is what you see mostly in like backbone architectures. And yeah, so that one's actually I refrain from saying best, but like that one's pretty common to use, Adam. And then cross entropy is how are we going to calculate our loss function? We're basically going to, given the distribution that we output in the actual like ground truth prediction, we're going to determine how wrong is it. Like maybe it detected like a dog cat, maybe it detected it was a cat, but it wasn't so sure that if it was a cat or not. The cross entropy will like adjust the loss function accordingly based off that distribution. And then we have our metrics, which we're going to use accuracy for now. For this type of basic task, accuracy is good enough. But when you're doing like localization, you would probably want to not look into accuracy or any type of information retrieval AI program. You might want to use like F1 score, recall, or precision, which is a more refined way of defining model's performance.
John, before you run it, you forgot a P in cross entropy.
Thanks, Hen. That's why you're here, bro.
You're
or that's why I'm well. I'm a dunce. All right, so let's make sure this is saved. You guys save this model and let's run it. Let's see how it works. Run this model. Let me make sure that I have what I need. I have my wave files, sick or not sick. Okay, chilling. And now we can run this model through the train method. Let me open up the train method so you guys can see like how it's training. Desktop, and we have our train. So one thing I should mention is that TensorFlow has this, TensorFlow Keras, I should say, has this class that we can inherit from called sequence. This allows us to batch up our data more efficiently onto the GPU if we have one. And by calling this, we can prep our batches to load into the GPU or load into the model in order to make super fast, accurate predictions. The sequence model has a method that yields the batches to the model, but in order for us to do that, we have to implement the get item. Like, what items are we looking at? We're looking at our batch indexes. So like out of our data set, where are they located in the batch? We're locating our images. So like our wave, not images, our sound files, like where is it located? How can we extract that for further use? We're locating its labels, where are the labels located? We need that. And then creating like XY, so X would contain our sound file information, Y will contain the labels. These are just vectors that we're going to pass through the neural network in order for us to learn accurate classifications. And this one just groups them and appends them to this neural network, or into these NumPy vectors. And then we have our train, which has like argument parsers. Seth Adams implemented all of this. I claim none of this work, but it's essentially pretty easy to follow through. We encode our labels, so our models can like determine, since it's only 2, we can just like look at 0 or 1, like sick or not sick, and that's how we're encoding it and fitting it into the label encoder. Our classes, which is just 2. And then we have this, we split it up. I'm using 10% of the data as test and train data, and the other 90% is going to be used for actual training. 10% is going to be used for testing. And then yeah, we just call the data generator, and then we call the data generator, and this should yield model performance. So we can just call this by doing Python training.py. Just to call this method. This method actually, this method actually calls our model. So it calls like our convolutional model, because we imported it over, where are you? Over here. So it calls like the model that we're using, and once it calls it, it then runs that model. It compiles it over here. And once we have that, we can just call the training module. All right, guys. I'm not that smart, as you can see. Requirements.txt. This is going to take. Shouldn't take too long. I'm just doing what I told you guys to do. I couldn't even follow my own directions, or I did, but like I deleted that virtual environment that I had. We have one more thing in the chat. Yep. Hey, I am a part of the biostats department at FIU. What are you studying at the moment? Ooh, that was sent to me privately. I'm so sorry. I'm just looking for questions to answer in the meantime. Well, just in case, for those who are who want to know what I'm studying computer science, minor in mathematics. I do a lot of this stuff. Like I'm self-taught a lot for machine learning. I find like it's pretty cool, like teaching a program how to be more like independent and make choices for itself. I find like the hard coding culture is kind of like not conducive, especially like as like the workforce is becoming more automated. One thing I should note is like kind of like an amateur tip, is like try your best to learn these models, even if it's on like a black box, like high level overview knowledge. I believe this is going to be like more like kind of like how data structures is used to solve problems. I believe it's going to become more normalized for us to use certain machine learning architectures in order to tackle stochastic problems, problems that may not have a definitive answer. Say you're working for the FBI and you want to track like terrorist groups. You can't say for sure a terrorist event is going to happen. You can only use predictions or stochastic based models in order to develop this inference or insight into the future in order for us to like position ourselves to be more prepared. COVID-19 will be a good example of that. Yeah, Alex is 100% true. It's becoming a buzzword. Like it's kind of cringy, like the way people use machine learning. Like is it machine learning to like get extra funding, but in reality they're just calling scikit-learn. Like that's not machine learning. I mean it is, but It's not real machine learning. Actually, hopefully this finishes soon. For those in the chat who are following along, can you guys give me some feedback of like if this is running for you? I just forgot to install the requirements .txt. You can do a thumbs up. Oh, here it is. You can do a thumbs up if it's running for you guys. If no one's coding along, do the clapping emoji so I know like, okay, I'm the one everyone's like kind of waiting for. Oh, I forgot. Did I forget? So like I mentioned in the beginning, I think I mentioned this. We just want, like when we open up, like we downloaded the cough and non-cough, it's split up into test and training sets. Take the test set for now because the training set is too big. We don't have time to train the actual training set. We're just going to take the small test set and train this to see that it is actually improving in performance. Yeah, so just take the non-sick and non-sick labels from the test set of the downloaded file and then put that into the WAV files folder. And then once that's done, we're good to go. Another thing that I should mention is make sure, like you want to create like a folder called clean. Yeah, you want to create a folder called clean. I should actually done this first. So we're going to call like our feature extraction. I thought I did this. I thought I did this on the GitHub, but apparently I didn't. Create a folder called clean and just run the cleaner. This shouldn't take too long to run. Yep, see, it took a couple seconds. And then what this does is extracts the features that we're looking for and then puts them into their appropriate folders. Yep, so that's what that does. So now we have that. And now we can run our training module if I typed everything correctly. Train. I usually call it trainer when I do these types of projects. Called train.py. This is going to take roughly 19 minutes, and we are over time right now.
Well, John, if in the meantime, if you want, we can talk about like some other stuff. I just remembered that we have the script that that produces the plots that we worked on, but
yeah, can you show the plots? So like once you do this correctly,
let me send it.
Yeah, send it, and send it to wherever you want to send it. Maybe you want to send it to me, I'll show it. And then yeah, the plots are a pretty good example. X.shape. So what's the issue here? So sorry guys, this ran. I went through this so many times when I was running. Of course, during the final, it's not running. Oh, yeah, I think it's inconsistent. So 5, so 7, max. So com2d is 7. Then we have 2. Then we have 5. Wait, 1, 2, 3, 4. Okay. Yeah, you guys want to copy this one more time. I know it's missing. Let's see. I knew this part was. I just was rushing through this because I'm a slow typer. We want to add 16 to this actually. 16. So we have 5, 2, 3, 2, 3, 2, 3, and 32, 2. Yeah, this should actually work. So like make sure like the input feature vectors are the same across, so that's why like 16 has to be like that in. Let me make sure this is saved. All right, so this is what I'm going to do. I'm going to run this actually on another example that I have. I ran this. Let's hope Let's pray that I have it.
Yeah,
I ran this.
errors are good when you're learning. I mean, if you ever come across this problem, then you know it's pretty common, and
True,
that's how you learn.
But let me go back. If you guys have time, I'm just concerned that I'm wasting people's time. This, I call it this, so like, I know where it is. I have like a bunch of files, I don't know organized. But CD audio processor, directory into here, train. What was the error again? The error was something.
Hey, why don't you activate your windows?
Activate my windows. Okay.
I'm just joking.
Let me see.
I still haven't activated mine either. It's been like 3 years, I think.
Bro.
Just use the KMS, man.
Man, I wish. What do you mean activate windows? Like I'm kind of confused. Sorry.
Look at the bottom right of your screen.
I was just making.
Yeah, we're teasing. I mean, I have it too. It's fine.
Oh yeah.
I mean, my Windows is activated, but like that thing does bother me eventually.
Okay, continue. Go ahead.
Okay. Yeah, it's good to know that you guys are paying attention. Root 4, same, G, same. So we go 2, 3, 32, 2. Sorry, I'm just kind of like mapping, so forgive me for being quiet. 3, 2, 3. Let's start from the top. So we pass in 8, kernel 7, kernel size. You know what it is? I'm pretty sure like it's probably like watch it be like something like I didn't name one of the parameters correctly. That'd be hilarious.
I'm checking, so.
Yeah. Oh no, this is what it is. I forgot to feed an actual input. Forgive me, guys. I'm like on another planet right now. Now this shit's on.
Sorry for laughing there.
Yeah, no problem. It is funny. It's funny to laugh at people.
I was gonna make a quirky comment about how this is going so well, but then it's like you were just so focused. I didn't want to interrupt you.
Yeah. Yeah, no problem, bro.
It looks beautiful, man.
Thanks, man. Thanks, dude. My dude.
And all this damn code.
Yeah, man. It's kind of a lot to digest, but once you actually know what's going on, it's like, oh, it's just tedious. Like,
I'm still just trying to get what's going on, but at least now I'm getting it better. Which is good for me. Yay.
Same problem here. Yep, I'm that guy. I'm that guy that makes mistakes, like in crunch time. So, but at least we're chilling.
Yeah, I'm the same here, actually. I doubt that would change. Oh my god.
Is there?
All right, I'm going to mute myself again. For the
Okay. Someone had a question?
No, I just want to know a Brad call.
Brad call.
Yeah, Brad call. All right. Well, he's not here. Well, I'll wait for him.
Okay. Tens are OP, and then we're looking at something is up, and I don't know what it is.
Well, John, I mean, we already have.
Yeah, can you show the thing? I'm gonna pause the screen for now. I will figure out the error, and Hermes is gonna show like once it's actually computed.
It's on my other computer, John.
Oh,
so,
it is?
Yeah, so I sent it to you on Discord, the actual script. You
Okay.
should just run it and it should be fine.
Okay. Okay. But the script isn't the script. Can you just send me the CSV actually, or actually I can just open the CSV because the script doesn't have its thing.
Yeah, I can send you the.
So actually, when we run this, we actually get like.
I'll send it to you.
Yeah, can you send it to me? Sorry, I started the training earlier and then I stopped it midway. So when we run this, we can go method. So this is what happens in live coding things, especially if you're not used to it. But this is my first time doing this, so hope you guys are easier on me. Method. Excuse me.
I sent it.
You sent it? All right. Cool. I don't want to waste you guys' time trying to figure out what went wrong. So I ran this model before.
Yeah, not to say anything right now, but
Wait.
the React workshop is currently going on right now. Just
Okay, yeah, I encourage you guys, if you guys are into that, to go to the React workshop. But
Yeah,
like as we can see, we get like 62% accuracy, but our loss is still pretty high. The reason being is because, like I said, we just took from the test data set. It's not that big. It's not that like relevant for us using the test data set. So that's why we're using the test set for now.
I just joined in. What are we making here? Just curious.
Just in the neural network. That's what we're doing.
Neural network?
Yeah.
Okay.
Yeah.
Thank you.
Oh, you guys. No one's telling me this. No one is telling me that. Sorry, guys.
oh my
It's been a
god.
long day.
I think we've all had a long day.
Yep, we did.
I mean, especially for those who are actually making a project for this hackathon.
I am actually helping my friend.
Oh, well, yeah, cool. I'm just here for the workshops personally.
Well, I'm helping my friend. Plus, we're trying to learn this even better.
Cool.
So padding is pool size.
Still kind of weirded out that this is going to be in part of a recorded video.
Ooh.
I mean, to be honest, like this is just the reality of like coding.
Oh yeah.
And we're all FIU students here. Like, no sweat about it.
Yeah, this will happen to anybody. It's happened to me before.
Yeah, exactly.
Yeah. Oh wait, I do have a question for the recordings. Where are they going to be posted? Because I definitely want to watch this lecture and I think maybe the Python data science.
Yeah,
later.
it's gonna be posted on the YouTube. Just give us a few hours to process the videos because it is a lot of data, and then we'll have it up there. If you want the link to the YouTube, I'll send it to you now. Okay.
Is it gonna be in
We'll probably announce it on the Discord, but the videos are gonna be on our UP YouTube channel.
Okay. That makes sense.
Yeah.
That's nice.
Right. I didn't say that, did I? Or did I? No, I didn't say it. It's because I was naming them all padding. This should work now. And 2 times should be. I'm naming stuff the same. That's the problem.
Isn't it lovely just how nice it is? Just
Yeah, it's a nice night.
nice night.
It's not raining tonight like all the other nights.
I think it was. Well, I guess it was supposed to. I think. I thought.
Yeah, I think that's what they were saying.
It rained yesterday. Acid rain.
Acid rain.
Yeah, it had a smell to it.
Oh,
Mm. I mean,
I'm-
like that rain that happened, like, because due to rain that happens, like,
Not like nitrogen,
oh,
but I'm in Broward, so like I guess
Oh.
that's why they had the curfew. I guess.
oh, yeah. I hadn't heard anything about that. I'm living in Miami-Dade, so.
I'm from Miami-Dade. I went to FIU.
Wait, what do you mean you went to FIU? You're not
Well,
in FIU anymore?
I graduated.
Oh. Okay.
I'm here for the class.
The work. So same as me.
Oh my god! At least I'm not alone.
Oh please, oh please, like everyone here was gonna actually do a project, or be active in making a project.
all right. Sorry, my bad, guys. Just adjusting things. I wasn't consistent enough on this.
There's one thing the hackathons are for. It's not about. It's for learning to code better.
That's
Yeah,
what I'm
that is
doing.
true.
Whether it's through whether through getting knowledge through the workshops or doing it on your own with a freaking project, whatever floats your boat.
I love it.
You
Oh,
like?
and you guys are on 64-bit. Thank you. Someone noticed.
Someone noticed what?
I mean, a lot of people are using 32-bit Python.
Oh yeah, yeah, man.
And
Oh.
we're
I
on-
mean, I guess people are using that because it's lighter weight. I don't know. I'm just making a guess here.
I mean, I guess it just exists because 32-bit OS architecture still exists technically, probably.
they're easier, but it's whatever.
Yeah, but I mean, yeah. They just exist because convenience. In case I'm pretty sure like the newest computers are all 64 based architecture.
I really think that Chrome is on 32-bit.
Chrome's a fucking web browser.
Let me do this. Let me do this verbose.
Yo,
So
Trout.
we're gonna do source. Yeah, let me do this verbose. Let me look at the arguments. We're going to do this like this. We're going to do sample rate or not sample rate. We're going to do source root. And we're going to copy where that wave file is. And we are going to do dest root. And we're going to copy the same thing, but instead of wave files, we're going to do sorry, things in the way. The sharing the screen thing is in the way.
I just realized you're using Anaconda right now.
Yeah, Anaconda font.
Oh. Yeah. I forgot to mention. Well, no, I was gonna mention. I was gonna mention this like a Discord or something, but thanks to the lovely help of the guide in the Python for data science, I finally have an actual Python path that isn't like in Conda.
Really?
Yeah. I just downloaded Python 3.84 and now I have it.
Nice.
So now and I'm pretty sure now it now actually will work as code.
Guys, I'm going to stop the meeting here. We're 25 minutes over.
Yeah.
I'm going to figure out what I did wrong. I'm going to record it and then send it in the chat, a link to it. Sorry, I couldn't get this up and running. I did this like 3 times today, and it was running perfectly. Of course, it's just
and luck has it that it would fail right now.
Don't worry,
Yeah.
man. You'll figure it out, man.
Thanks. But do you
It
guys have any
happens.
questions like overall?
Oh no, you did no.
Overall, but
That's right. He did amazing.
I
John,
joined the meeting really late, so I kind of got lost from the beginning. So
okay.
well then watch the video so that way you don't get lost anymore. Because trust me, I got a little lost here too. But also, well, that's mostly because of all the code that you've been typing.
the COVID you said, or coding.
Does anyone have any questions though? Like maybe you want to ask me like.
I
questions
do.
about-
I do actually. What kind of processor are you running this on?
What define process?
Processor. I crashed 1 second. Said
Yeah,
that.
that's just a story of our lives. What do you mean by process? Oh, processor.
Yeah, CPU.
Okay. Using an AMD processor, the Ryzen 27.
Can I ask like why though? Like, is it better? I mean, in my opinion, I've been in the tech industry a lot. I find that AMD had a problem with overheating, and it still does, and it's scary.
But to be honest, AMD is actually they're pushing, from what I understand, they're a little bit more flexible with their architectures. They're using multi-threading a lot more, which the whole parallel architecture is becoming more ubiquitous. I actually find the inverse.
Look at that.
I actually find the inverse. Intel overheats a lot, actually.
Intel, maybe my Intels don't overheat because I run the AC really cold. But I've fried so many AMD processors, and I've had people return them on me as well.
Yeah.
And
I don't know.
Yeah.
I don't know. Just AMD, like as a company, is
it's a great company. I used to
It's a great
it.
company, but like they're not. I like using tech that seems like they're at least trying to like go cutting edge. I don't like complacency. So that's just me personally.
Mm-hmm.
Yeah.
I completely agree.
And speaking of complacency, yeah. Sorry, I got interested in this too because my sister got a new computer and it's an AMD-based computer. So
The reason what turned me off of the AMDs,
mind you, she's sorry.
Sorry.
No, continue.
Brad is here. He just 10-4'd me. All right. AMD, I didn't like when they went with HP. They really cut back. They were really laggy and slow, and it was a huge disappointment because we were getting a lot of computers that were just lagging with the AMD processors. And I think it was the HP 2000s.
Really?
Yeah, they use a processor called the gotta remember. I gotta grab my laptop.
Okay. But for those,
John,
yeah.
sorry to interrupt, but just so that if some people want to know, the GitHub for John is right there. My GitHub is right there, and QR, you can scan it for our LinkedIn's if you have any questions or anything. But yeah, continue, John.
Yeah, I was gonna wrap it up. I was gonna say, when I debug this, I'll let you guys know what I did wrong.
Okay.
But as you can see, there's like a delicate balance, like with programming these type of things. A lot of things can go wrong because intrinsically it's a very complicated process and like building these things up from the ground up. But
networks are complicated architectures.
It's AMD E300.
Yeah. But if you have any questions like ML related, I'm always open. Adrian Perez, he's in this chat. Like this dude knows way more.
Well, I think he left.
No, he's here. I see him.
Really?
Yeah.
I checked earlier and he was not here.
Well,
Well, Rad never 10 forward, but he's here. He's still watching.
Maybe he just came back or I just missed him.
Yeah. Well, we can message me, myself, Hermes. Hermes is learning. One thing I should mention, he didn't mention this, but Hermes is that dude. He's a high schooler.
Yeah, that's
He's a
right.
high schooler doing this.
Oh man.
You're learning from high school right now?
I can speak up.
I'm dual enrollment.
Yeah, he's in
Oh,
I'm
a unique dual enrollment.
my friend did that, but he did it for aviation.
nice. Yeah, no, it's just like I'm full time on FIU normally. So
That's good. And keep it up, man.
Thank
You'll get it. You'll get it there. Like you'll graduate and you'll be like, I made it.
I did the same thing before Miami-Dade College.
Miami-Dade, I actually was gonna go there.
Alright, guys. I'm actually gonna end this meeting, but
I mean, mind you, I'm still in college because
All right,
the
cool.
thing just
Yeah.
hey,
thanks for showing up. I know it was all over the place, but feel free to message me. I'm gonna upload the code on GitHub. I'll link the finished code on the workshop channel, and then you guys can probably use it like for your own classifications. Maybe.
yeah, and I hope you at least learn something. Hopefully, something that you can use in the hackathon.
I help people understand some of the content.
Yeah, I
That's why I typed up crap in the first place.
wish you all good luck, and hopefully you win first prize.